Okay, this is lesson 4 of our circuit analysis lessons, and I want to draw your attention to this example here. So we've got 2 current sources and 3 resistors, and I want to solve this circuit. And by that I mean I want to know the voltage everywhere. So I want to know the voltage across each resistor, the voltage across each current source, and I want to know the current everywhere. I've already got the current in this branch and in this branch, but how about the current through the 6 ohm resistor? How about the current through the 4 ohm resistor and the 2 ohm resistor? So if I know all of those things, if I know all the branch currents and I know the voltage across every component, then I essentially have solved the circuit. I can get the power in each component through a straightforward manner at that point. So, so far, we have the following methods of analysis, and I'll put them in this order. This is the order that we learned them. Ohm's law. Now, you cannot use Ohm's law in this circuit. For Ohm's law, of course, V equals IR. I is the current through a resistor, V is the voltage across a resistor. You do not know any of the currents through the resistors. You know that this 5 amps comes this way, but you don't know how it splits. You don't know how much goes this way, and you don't know how much goes this way through the 2 ohm. Same thing over here. This 10 amps you have coming up here. 5 of it goes up here, but you don't know how much goes through the 4 ohm, and you don't know how much goes through the 6 ohm. So you cannot immediately apply Ohm's law. Second, we know Kirchhoff's laws. Okay, and well, we are going to use Kirchhoff's laws. We are actually going to use Ohm's law as well, but you cannot immediately apply Kirchhoff's laws either. We don't have just one loop here, so you can't immediately apply Kirchhoff's voltage law, and we don't just have two nodes, a parallel circuit, so you cannot just immediately apply Kirchhoff's current law either. Third, in the last video, we worked on combining resistors, resistor combinations. Okay, and what went along with that was voltage and current division. So current division could be nice here. Current division. It could be nice because we want to know how does the 5 amp source split, how does the 10 amp source split. But current division only applies for when resistors are in parallel. Okay, and so if we identify the nodes, here's 1, here's 2, here's 3. Notice that there are no parallel resistors there. A resistor is in parallel with another resistor when they are connected to the same 2 nodes. So if we called this node 1 up here, maybe this node 2, and maybe this node 0, you see the 4 ohm resistors connected to nodes 1 and 2. Well, no other resistors are connected to 1 and 2. This is connected to 2 and 0. This is 1 and 0. So no resistors are in parallel there. The 4 ohm resistor is in parallel with the 5 amp source, but that doesn't do us any good for resistor combinations. All of this is to say that what we have so far is insufficient to solve this circuit, and so we need something else. So we're going to add another tool to our toolbox today, and that is nodal analysis. So that's the subject of this video, nodal analysis. And I'm actually going to break nodal analysis down into 2 videos. This video is part one, and that's going to be circuits without voltage sources. How many circuits have no voltage sources? Not many. Okay, but nevertheless, the examples in this video will serve as a nice introduction to nodal analysis. And then part 2 will be the next video, and we'll introduce voltage sources there. Okay, so nodal analysis is kind of our newest tool, and the great thing about it is that it applies to every circuit that you will see in this course, linear circuits. It applies to every linear circuit you will see in this course. And you say, well, why don't we just learn that? Well, the price you pay is that it's actually the most complicated. There's a lot of math that could be involved in using nodal analysis. So at first we want to try to use Ohm's law or Kirchhoff's law or combining resistors. And if none of those work, then we want to try nodal analysis. Okay? And there's kind of a systematic procedure for nodal analysis, and so we'll just start with that procedure. Step 0, I guess, say. Step 0, identify the nodes, which we've already done. Identify the nodes. Okay. Choose one node to be the reference, right? To be ground. And label the others. Label the other nodes. Label the other node voltages. Okay, so in this circuit, I've already called this node 0 down here, so I'm going to choose that one to be ground. And I've already chosen this node to be 1, and so we'll label the voltage at that node V1. So whatever we find V1 to be, maybe it's 9 volts, that's 9 volts relative to this node, okay, because this is our reference node. And similarly, I'm going to label this voltage at this node to be V2. So identify the nodes, choose one node to be ground, label the node voltages. That's what we've done. Okay, and these are our unknowns. So kind of in red here, I'm going to say, well, n nodes, right? 1 is ground. That leaves n minus 1 unknowns. So, for example, in our circuit, we have 3 nodes. Okay, 1 is ground, and that leaves 2 unknowns, V1 and V2. So these are what we're going to be solving for. Okay. As step 1, then, after we've done that, just going to guess the direction of all unknown branch currents. Okay, and if you've really been paying attention to the last 3 videos, you should be convinced now that the direction, or our guess of the direction, does not matter. You will eventually end up with the correct answer. So I'm just going to guess that the current here is going down. I guess that the current here is going down. We'll say the current here is going to the left. And all the other branches, see, this branch is already given that it's going to the left. This branch is already given that it's going up. So I'm good. That's the end of step 1. Okay, step 2 is kind of where the magic happens here, and we are going to apply KCL at each of the non-ground nodes. Okay, and here's the key. Write, okay, remember KCL is Kirchhoff's current law. The sum of the currents entering is equal to the sum of the currents leaving. But write all unknown currents in terms of the unknown voltages that we've already decided we're going to solve for. Voltages. These are our unknowns, the voltages. In nodal analysis, just as the name suggests, nodal. So node voltages are the unknowns here. Then step 3, solve the n-1 equations. Okay, because in step 2, if we apply KCL at each non-ground node, we have 2 non-ground nodes, then we're going to have 2 equations, and we have 2 unknowns, so we can solve those n-1 or 2 equations in this example. And we'll say that's it for this procedure. Okay, and you say, well, what about the currents then? Well, once we know the voltage at node 1, and once we know the voltage at node 2, then we know the voltage across the resistors, and then we can apply Ohm's law to get the currents through those resistors, as you will see in this example. Alright, so here we go. Let's do KCL at node 1. KCL at node 1. So based on my guess here, and I'm going to label the currents so I can reference them. We'll call this I1, call this I2, call this I3. So based on my guesses of directions of the currents, KCL at node 1, I have 5 amps coming in, plus I have I2 coming in, equals the sum of the currents leaving, and at node 1 the only current I have leaving is I1. Okay, but remember step 2 here is apply KCL, and that's KCL, but write all unknown currents in terms of the unknown voltages. So here are my unknown currents, I1 and I2, and I want to write them in terms of the unknown voltages. So we're going to use Ohm's law to express I2. I2 is the current through the 4 ohm resistor going from right to left. So Ohm's law would say that that is V2 minus V1, the difference from right to left, divided by the resistance, 4 ohms, equals I1, and so that's the current through the 2 ohm resistor going from node 1 to node 0. So Ohm's law would say that that is V1 minus, and I'll show explicitly the 0 there, V1 minus 0 over 2 ohms. Now we're going to end up solving this equation. Okay, so it might benefit us a little bit to simplify this. So if I multiply the entire equation by 4 ohms, then I get 20 volts plus V2 minus V1 equals 2V1. And if I move the unknowns to the right, I've got 20 volts equals 3V1 minus V2. And I will put a star by that. A couple stars, just so it stands out. We're going to need that later. We'll come back to that, and let's do KCL at node 2. Okay, so I look at node 2, ask myself what currents are entering, what currents are leaving. Okay, well, I see the 10 amp source is entering, and that's it. That must be the sum of the currents leaving, and I see the 5 amp source is leaving. I2 is also leaving. I3 is leaving as well. So I write, again, the trick is to write those unknown currents in terms of our unknown node voltages. So I2 is, again, the current through the 4 ohm resistor going right to left. So Ohm's law says that's V2 minus V1 over 4 ohms. We used it in the previous equation. I3, the current through the 6 ohm resistor going from top to bottom, that is V2 minus 0 over 6 ohms. Alright, now I can move the 5 amps over to the left. That would make 5 amps. And multiply by the common denominator here, which is 12 ohms. So if I do that, I'd have 5 amps times 12 ohms. So that is 60 volts equals, then I would have 3 V2 minus 3 V1 plus 2 V2. Again, if I'm going too quickly, feel free to pause the video as necessary. Alright, now I will put it in the same form as our first equation that's starred up there. So this is 60 volts equals negative 3 V1 plus 5 V2. And we'll put some stars by that guy, just so it pops out at us. We need those two. Now, that's the end of step 2 over here. Okay, I notice I have 2 equations. Well, now I need to solve this. So this one is pretty easily solved. There are only 2 equations, so use your elimination or substitution or whatever you like. In the next example, I'm going to give you in 2 examples from now, I'm going to give you 3 unknowns, 3 equations, and so I'm going to give you a general method that you can use to solve these equations called reduced row echelon form. But for now, solve it. I see the most easiest way, I think, is just to add those 2 equations, and the V1 drops out. So if I add those 2 equations, I would have 80 volts on the left equals 4 V2. So the V1 drops out, and I divide by 4 there, and I have 20 volts is equal to V2. So that's part of my solution here. Now if I want V1, I can go to any of the other equations. Let's go to the first one. So that would be now 20 volts is equal to 3V1 minus 20 volts. Is that right? Excuse me for a second. Volts. Yes, yes. So now I want to solve for V1, so I add the negative 20 to the other side. So this is 40 volts equals 3 V1. And so that implies that V1 is 40/3 volts. That's the end of step 3, solve the equations. So there are our 2 unknowns. 40/3 and 20 volts. So I'm going to label those in my picture. Okay, so V1 is 40/3. V2 is 20 volts. And again, that's with respect to this node down here that we're calling 0. And I'm going to erase a little bit here. Let me erase this guy. And now if I want to get the currents, so that's the end of nodal analysis, but let's solve the circuit. I'm going to get the currents. So if I want I1, Ohm's law says that would be, if I1 is going from top to bottom, we guessed, so that's 40/3 volts minus 0 divided by 2 ohms. So that is 20/3 amps. And notice it's positive. It's positive. That means our guess of the direction was correct. Okay, if I want I2, Ohm's law says that's the voltage at V2, 20 volts, minus the voltage at V1, minus 40/3 volts, over 4 ohms. Okay, so if I get that, so I need a common denominator in the numerator of that fraction. So 20 volts is 60 volts over 3. 60 over 3. So 60 volts minus 40 volts is 20 volts. 20 volts over 3 divided by 4 ohms. That's 5/3 amps. Again, it's positive. That means we guessed the correct direction of I2. And I3, Ohm's law says that would be 20 volts minus 0 divided by 6 ohms. So there is a factor of 2 there, so this is 10/3 amps. So I've got now all of the voltages, I've got all of the currents, so I have essentially everything I need. If I was interested in a power calculation, let's say the power supplied by the 10 amp source. Okay, power supplied by the 10 amp source. So how many volts do I have across the 10 amp source? Well, V2 is 20, this node is 20 volts, and this guy is 0. So I have 20 volts times the current through the device is 10 amps. Okay, so that gives me 200 watts. And notice the current is going, it enters the lower potential and leaves through the higher potential. So it is indeed supplying power. So we could just tack on a negative sign there if we wanted an algebraic equation with the power. So it's got negative 200 watts of power there. All right, and just another example. Let's say we want the power absorbed by the 4 ohm resistor. Okay, well, what's the voltage across the resistor? So that's 20 minus 40/3. So again, 20 is 60/3, so this is 20/3. 20/3 volts times the current, that's the current through that resistor is I2, which is 5/3 amps. Okay, so this is 109 watts. And notice, again, the current is going from high potential to lower potential, so it's absorbing. All right. So we've kind of analyzed that circuit to death. That's about as much as you can do with that circuit. So I'm going to erase this now. Again, feel free to pause the video if you need, and we're going to go on to another example. Before we do that, let's keep the process though. So I'm just going to delete everything but the step-by-step procedure. Okay. And we'll move the step-by-step procedure up here. Alright, so let me give you another example. We'll start with, again, current sources, because we're not looking at voltage sources at this time. Okay. So here's my circuit, and maybe the question is maybe not just to solve the circuit, but find the power. Or maybe here's the question: is the 12 amp source supplying or absorbing power? Remember, sources can absorb power, just like a battery can be charged. Is the 12 amp source supplying or absorbing power? How much power? Okay, so there's the question. All right. Well, our tools here to use, first our Ohm's law. But again, so this 3 amps comes in and you don't know how it splits. 12 amps comes down here, you don't know how it splits. So you don't know the current through any of those resistors. You can't use Ohm's law. Kirchhoff's law is our next line of defense. Well, we don't just have one loop here, we've got several. And we don't just have 2 nodes, we don't just have a parallel circuit, so we don't want to use Kirchhoff's current law either, not directly anyway. No resistors are in series or parallel. Notice if we identify the nodes, here's a node, call that node 1. Here's a node, call that node 2. Here's a node, call this node 0. None of those resistors are in parallel with one another. That is, they don't have the same 2 nodes. Also, we didn't address this in the first example, but none of them are in series either. Okay, to be in series, you have to exclusively share a node. So, for example, the 6 ohm resistor and the 7 ohm resistor share node 2, but not exclusively, because the 12 amp source also shares that node. And I want to emphasize this again. The 2 ohm resistor and the 7 ohm resistor are not in parallel. Not in parallel, despite them being drawn kind of in parallel. They are not. They are not connected to the same 2 nodes. Okay, so none of those things work for us then. So we have to resort to now nodal analysis. So step 0, identify the nodes. We've done that. Choose one node to be ground. I'll just choose the bottom. It does not matter. Label the node voltages. Okay, so we'll call this V1, call this guy V2. So that's the voltage at this node V1 relative to this node. And V2 is the voltage at this node relative to this node. Alright, step 1. Guess the direction of all unknown currents, branch currents. So I'm just going to guess that this guy is going down, and we'll call that I1. And I'm going to guess that this is going to the left. Call that I2. And I think this current is going up, but I'm going to guess that it's going down. Hopefully I'm wrong, because I just want to show you that it doesn't matter. It doesn't matter if I'm wrong or not. So I'm going to guess it's going down. Okay, now step 2, apply KCL at each of the non-ground nodes. Okay? So let's do KCL at node 1. Alright, so I've got the 3 amps coming in. I also have I2 coming in. And I've got I1 leaving. But I want to write all of those unknown currents in terms of the unknown voltages. So I2 is V2 minus V1 over 6 ohms. V2 minus V1 over 6 ohms equals I1. And I1 is V1 minus 0 over 2 ohms. Alright, and then I might want to simplify that a little bit. Let me multiply by the common denominator of 6 ohms. So when I do that, I get 18 volts plus V2 minus V1 equals 3V1, and I'll move the unknowns to the right. So this is 4V1 minus V2 equals 18 volts. Alright, and I'll put a star by that, a couple stars by that guy. Now let's do KCL at node 2. Alright, node 2, I've got none of the currents are entering. Okay, that's good. That means that one of my guesses is wrong. So 0, a big goose egg there, is entering. Leaving then is the 12 amps plus I2 plus I3. Now I want to write the unknown currents in terms of the unknown voltages. So I2 is going from right to left in the 6 ohm resistor. So right V2 minus the left V1 over the 6 ohms plus I3 is V2 minus 0 over 7 ohms. Alright, so the common denominator here is what? 42? Oh, there's got to be something better than 42. 28. Nope, I think it is 42, unfortunately. So this is 0 equals 42 ohms times 12 amps, whatever that is, plus 7 V2 minus 7 V1 plus 6 V2. And I'll move this, I'll put it in the same form as this equation. So I'll move the constant term over. So this is minus 42 ohms times 12 amps equals. And I've got minus 7 V1. Okay, and plus 13 V2. And this is getting ugly. I've got a lot of prime numbers there. So there's nothing I can do there. That's my equation. Alright, so I need to solve these two equations simultaneously. So however it is you want to do that is fine by me, as long as you do it correctly. So again, when you only have two equations, probably the best thing to do is just to eliminate one of them, or solve for one of them in terms of the other. So for example, if I solved this equation for V2, I would have V2 equals 4V1 minus 18 volts. Right? And then I can plug it into this equation here. So this would be minus 42 ohms times 12 amps equals minus 7 V1 plus 13 times V2, but V2 is this thing, 4 V1 minus 18 volts. Okay, so now I need to do some math here. So let's just keep this right now as 42 ohms times 12 amps equals minus 7 V1. And then when I distribute the 13 in, I get 52 V1. And I get 13 times minus 18. So that real quick, 13, actually I'm very slow in math. That is 104 there and 13 there. So it's 234 minus 234 volts. Okay, so I've got minus 42 ohms times 12 amps. And then when I combine the 52 and the minus 7, I get 45 V1, right? Minus 234 volts. And let's do this guy then. 42 times 12. 42 times 12. That gives me 408 and 42. So that's 504. Okay, so I've got minus 504 here, and when I add the 234, I'll have, so I've got, let me write this down, I've got minus 504 volts, then plus 234 volts equals 45 V1. Okay, so let me do this problem here. This is a 234 minus 504. So it's 0, 3. Oh, excuse me, sorry. Let me back up. Let me erase that. So we're in the negatives here. So this is 504 minus 234. 0, 4, 7. Okay, so we got minus 270 over there. So this equation boils down to minus 270 volts equals 45 V1. Okay, so there's a factor of 5. So if I divide by 5, and there's a factor of 9, yes, that's good. So if I divide by 5, I would have 55. 54 minus 54 equals 9 V1, and if I divide by 9, I get V1 is equal to minus 6 volts. Minus 6 volts, good. That worked out nicely. Alright, and now if I want V2, remember this equation here? V2 is equal to 4 times V1, which is minus 6 volts, minus 18 volts. So V2 is minus 24 volts, minus 18 volts, okay, minus 42 volts. V2. Okay, this is just all math, right? This is an electrical engineering course. Sometimes we have to use math. But don't get too concerned with it. I hope you can do it, but I'm not interested in teaching you math because that's not my job. My job is to teach you electrical engineering. So I'll label these voltages up in my diagram. So V1 is minus 6 volts. Don't be scared by the minus signs. This is minus 42 volts. Okay, the minus signs just mean that the node we chose as ground actually wasn't the lowest voltage. This is the lowest voltage. Okay, but remember that question? Is the 12 amp source supplying or absorbing power? Okay, we'll write answer. Well, take a look at the voltage across the 12 amp source. The voltage across it, well, this is 0. This is minus 42. Okay, so the voltage across is 42. 42 volts. Remember, this power equals V times I. That only gives us the magnitude of the power. We've got a difference of 42 volts and a current of 12 amps. Okay, we did that calculation actually. It's 504. 504 watts. Now the big question is that supplying or absorbing? Well, the current comes into the lower potential here, which is minus 42 volts, comes into the lower potential and leaves the higher potential. So this is the marble rolling up the ramp. So this thing is supplying the energy or the power for that marble to get up the ramp. Supplying. Okay. Okay, well, we're going to do one more example. Again, feel free to pause these videos as you need. Okay, and so I'm going to erase this. All right, and final example is going to be a larger circuit, and it's going to be a larger system, meaning there are more nodes, more equations to solve. 8 ohms, 4 ohms, 2 ohms, and we'll have a current source here of 3 amps. And we're going to have a dependent current source here. Yes, this works with dependent current sources as well. And we'll call this 2IX. And where is IX? Well, IX is here. Okay. This is a current source, but the current depends on whatever this current is. We can nodal analysis can handle that situation. All right, so let's identify the nodes. Here's one. Here's another. Here's another. And here's another. So 4 nodes minus 1 makes 3. So we'll have 3 unknowns and 3 equations. Let's call this node 0, node 1, node 2, and node 3. And similarly, let's say that this is voltage V1, voltage V2, and voltage V3 up there. Okay, so that's step 0. Now, guess the direction of the currents that are not given to you. So we'll just guess that this is going down, and we'll guess that this one's going to the left. And here we'll guess to the right. All right, so let's do KCL at node 1. Okay, at node 1, which, let me go back to the currents. Let me label them so I can reference them. This is I1, I2, I3. Okay, so at node 1, maybe you should pause it and see if you can write an equation on your own. But at node 1, the 3 amps is coming in, and the I3 is coming in, and I3 is V3 minus V1 over 4. Those are going in. What's leaving, IX is leaving. We're not going to write IX. we're going to write it in terms of the voltages. V1 minus V2 over 2 ohms. And let me simplify this by multiplying by the common denominator of 4 ohms. So on the 3 amps makes 12 volts. V3 minus V1 equals 6 V1 minus 6 V2. Oh, excuse me. No, that's not right. I multiplied everything by 4, so this is 2 V1 minus 2 V2. All right, and I'll keep the common. I'll keep the constant term on the left. And when I add the V1 to the other side, that makes 3V1 minus 2V2 minus V3 when I bring it over. All right, and I will star that one and move on. KCL at node 2. Okay, here's node 2 in the middle there. I've got, based on my guesses, simply IX entering, and IX is V1 minus V2 over 2 ohms. Leaving is V2 minus 0 over 4 ohms, that's I1, and I2, which is V2 minus V3 over 8 ohms. So let me multiply by the common denominator and put it in a form similar to our previous equation. Common denominator here is 8 ohms. So this is 4 V1 minus 4 V2 equals 2 V2 plus V2 minus V3. So in a form similar to the last equation, that's a 0 constant term. And when I get the V1 over, this is minus 4 V1. The V2s make, I've got 3 here, and then I bring the 4 over, so that makes 7 V2. And then I have it this minus V3. And I'll need this equation. Let me put some stars there so it pops. And finally, let's do KCL at node 3. And here's the interesting one here, because our current source, our constant current source, right? So entering node 3, and actually I should have circled all of this stuff. This is all node 3. Coming in is I2. Okay, I2 is V2 minus V3 over 8 ohms equals. This current I3 is leaving, V3 minus V1 over 4 ohms. And this current is leaving. This is 2 times IX. But we already wrote an equation for IX. It was V1 minus V2 over 2 ohms. You see, I don't want to write IX here, because that's another unknown, and my unknowns are the 3 voltages. So I need to write IX in terms of the voltages. So that's what I've got. So now I would just multiply again by 8 ohms is the common denominator here. So this would be V2 minus V3 equals 2V3 minus 2V1, and then this would be plus 8V1 minus 8V2. Let me get it in a form similar to the rest. 0 constant term. Okay, I've got a minus 2V1 and a plus 8V1, so that makes plus 6V1. Over on the right, I've got minus 8V2, and when I bring this guy over, that makes minus 9V2. And I've got a 2V3, and when I bring this one over, that makes plus 3V3. Okay, and this one, if I like, I can divide by 3 and make it even simpler. 2V1 minus 3V2 plus V3. And we'll put a star by that guy. Alright, now I'm going to show you a way to solve. We have 3 equations and 3 unknowns now. So your substitution and your elimination methods are going to be pretty tedious. But you do whatever you like. I expect you to be able to solve these 3 equations and 3 unknowns. I will give you a general way that will work for any number of equations, even the previous examples with 2 equations and 2 unknowns. I'm going to put these in a matrix. Okay, so this first equation, I'm going to take the coefficient in front of v1, so that's 3. And the coefficient in front of v2, I'm going to put next in a row. And the coefficient in front of v3, I'm going to put next in the same row. I'm going to draw kind of a dotted line here to show it like an equal sign. And that equals 12, the constant term. That's my first equation written as a matrix. So this guy is the V1 column, V2 column, here's the V3 column, here's the constant column. Alright, so let me put the next equation in there. This was a constant of 0. And we had a minus 4V1, a 7V2, and a minus 1V3. Finally, this third equation, I had a constant of 0, 2v1, minus 3v2, and 1v3. Alright, so now I need to solve this system of equations. And to do that, my preferred method is to use reduced row echelon form. Reduced row echelon form. RREF for short. So your graphing calculators can do this, MATLAB can do this. Basically what it does is it puts the matrix into a form that's more easily solvable. And so let me just demonstrate that to you. I have Java application ready to go here. So I'm at this website here, matrix.reshish.com/Gauss-Jordan elimination. So I'll start by saying that I want a matrix that's 3 by 4. So you see my matrix here. I've got 3 rows and 4 columns. So let me say set matrix, and I will just type in. I've got a 3, minus 2, minus 1, 12, negative 4, 7, minus 1, 0, 2, minus 3, 1, 0. And then I'll click solve. You didn't put it. Oh no. What did I do? Oh, sorry. Here, I put a 0 there. Solve. Okay, and out pops the solution. There it is. Now, if you're doing this in MATLAB, or if you're doing this in your in a graphing calculator, what you would see is not just out pops the solution, but you would see something that looks like this. Let me just write it down. And this is what you would see when you would put your matrix into reduced row echelon form. Now, what this means is, well, remember the columns, right? This was column V1, column V2, column V3, and the constant. Okay, so this first row says that 1V1 plus 0V2 plus 0V3 equals 24 over 5. In other words, V1 is 24 over 5 volts. And that's our first unknown, right? No unknown no longer. 4.8 volts. Similarly, our second equation says that V2 is 12 over 5. volts. Okay, that's again, that's 2.4 volts. 2.4 volts. All right, and finally, our third equation is V3 equals minus 12 over 5 volts, which is minus 2.4 volts. All right, what it's doing, there's an algorithm to solve this, and it's basically doing what we did for the two equations in the previous examples, but in 3, and so it just doesn't show you those gory details. Out pops the answer. So that's what we're interested in here. And so I've added those already to our circuit, and so you'll see that this, what we chose to be ground, is not the lowest potential. That is up here. This top node, top right node, is actually at the lowest potential. And so we've got the voltages now at every node, and so we could get the well, we could get all the currents. So for example, if we wanted I2, we can now use Ohm's law. I would say 2.4 volts, the left, minus the right, minus 2.4 volts, over the resistance, 8 ohms, is the I2. So this is 4.8 volts over 8 ohms, so that is 0.6 amps. Okay, that's the current I2, and it's positive, so our guess was correct. Notice that the current is going from the higher potential to the lower potential, as it always does with a resistor. The marble always rolls down the ramp if the ramp is a passive element like a resistor. How much power is that resistor absorbing? The power is I times V. So I is 0.6 amps. V is 4.8 volts. Okay, and so we do that calculation, and that would give us our wattage. Okay, again, and I want to emphasize something from the first video. Notice I used 4.8 volts here for the power in this resistor. I did not use 2.4. and I did not use minus 2.4. What matters is the difference in voltage across the resistor, or the component for that matter. So you could see how you could get all the other currents, and you could get all the powers and all of the devices. Now, don't get yourself in a tizzy over reduced row echelon form, okay, going from this thing to this thing. That was the way that I preferred. Your book uses Kramer's rule, which I'm not a big fan of, but you can use that as well. Whichever method you need to use to solve the equations is fine with me. I'm not interested in the method you use to solve the equations. I'm only interested in if you can solve them correctly and if you can get the equations to begin with. So if you can get these 3 equations that I've circled in red there, that's the electrical engineering part. So you've done a great job, and now this becomes a math problem. Okay, then we get our answers, and now it becomes another electrical engineering problem. How to interpret your answers, how to get the currents and all the powers, etc. Okay, so this takes practice. Make sure you're working on the homework. All right, and next time, in the next video, we're going to look at circuits with voltage sources in them. And we're going to have to modify this procedure just a little bit when we have a voltage source inside our circuit.